Today we will provide algorithms for these two decision problems for context free languages. The first one is that we need to determine, given a context free grammar G, if the language generated by the grammar infinite or finite. For this problem, so let us say problem 1 algorithm will provide a sketch So, you are given the grammar G, that is the input. So, first what we do is step 1, find from G its Chomsky normal form grammar G1. So, we know from the definition of Chomsky normal form grammar G that this grammar G1 that we obtain, the language generated by the Chomsky normal form grammar for the grammar G will generate the language LG except possibly one string, and that is the empty string, because recall that a Chomsky normal form grammar cannot generate the empty string. So, clearly G generates an infinite set if and only if G1 generates an infinite set. So, equivalently now therefore, we will look at is LG1 infinite. This is the question we resolve, where G1 is in Chomsky normal form. The way we do it, it is actually quite straightforward. We create a directed graph for the non-terminals of the grammar G1. So, let me define this. Consider the directed graph. And this, sorry, this is the non-terminal set of. So, let me clearly say what I mean. So, G has this graph. Now, this script G is the graph that we are building given the Chomsky normal form grammar G1. G has as vertices the non-terminal of G1. So, in other words, if my G1 was the set Vn sigma P S, the directed graph that we are building, that will have as vertices this set of non-terminals. That is what we have written, right. Now, from let us say a non-terminal A in G. So, now remember, now we can see a non-terminal has kind of two roles, one as a vertex of this graph G, of course, as a non-terminal of the grammar G1. So, from a non-terminal A in G, there is an edge to the non-terminal B in this graph that we are constructing if and only if there is a production A goes to BC or A goes to CB for some non-terminal C, right. So, what we are saying is this, in this graph that we are building, there will be an edge from a non-terminal A to non-terminal B if there is a production in which A occurs on the left hand side and B occurs on the right hand side of that production. Now, the claim is L G1 is infinite if and only if this graph G has a cycle. We need to, of course, for proving this claim, prove that if G has a cycle, then LG1 is infinite and vice versa. So, let us do these one by one. If and the proof idea is suppose the cycle, one cycle that we have in this graph is of the form, the cycle is from A1 to A2 to A3 AK and back to A1. Right. So, what does it mean? This means that from A1 you can derive some string which will have A2 in it. So, we can say that this first edge in the graph, this means that A1 derives, let us say alpha 1, A2, beta 1, right. And similarly, A2 derives alpha 2, A3, beta 2 and so on. AK minus 1 derives alpha k minus 1, AK beta k minus 1, and then because of this edge back we have that AK in turn derives let us say alpha k A1 and beta k, right. Now, the crucial point is, because the grammar G1 is a Chomsky normal form grammar, so this is something you can verify that it is not possible for each I alpha both, so let me write it this way, both alpha I and beta I are empty strings. Okay. So, in fact, it is quite easy to see, at least in one, for example, in the right in the beginning, when we say A1 derives alpha 1, A2, beta 1, and suppose both alpha 1 and beta 1 they were empty strings. So, that would mean what? That A1 derives A2. Is that possible? Because that is not possible in Chomsky normal form grammar, because remember that Chomsky normal form grammar does not have unit productions as well as epsilon productions. So, in the absence of unit productions and epsilon productions, A1 derives A2 is just not possible for two distinct non-terminals A1 and A2. So, basically from this what we get, if you see what is happening is that from all this we can say A1 derives some alpha AK beta, we just this in this A2 I substitute this and so on, and then then this AK I can, of course, for this AK I substitute this. So, what will happen? Alpha k A1, right, then beta 1 beta k beta k beta 1, right. So, as before, both of these can't be empty, right. So, that means A1 derives A1, a string with A1 and plus some non-empty things. Now, both these things, because again it is the grammar is Chomsky normal form, it is not possible that both of them finally they derive the empty string. This both of these alpha k together could be a string of terminals and non-terminals, but it is not possible that both these strings derive only empty strings. So, in that case what it means is that I will have A1 deriving something, let us say x A1 y. Finally, when x and y, I should be able to find terminal strings x and y such that A1 derives x A1 y, where both x and y are not empty, right. And now also, because see this fact I am getting because of the cycle, right. Now, from another source we have another fact about A1, that A1 does generate some terminal string which is non-empty. Why? Because A1 is not a useless symbol. So, A1 has to derive some terminal string, because A1 is a non-terminal of the Chomsky normal form grammar. So, now put these two together, what does it mean? Just see, this is right away, it is very simple, that from A1 you can get x A1y, then you can just keep on doing it as many times, this A1, then you can again replace it by x A1y. So, you will get xx A1yy, then xxx A1yyyy, something in that form of our UVWXY theorem, and then finally this A1 you can rewrite by the terminal string z, and so therefore A1 will derive what? X I z y I for all values of I greater than equal to 0. And what also we know, so we can say A1 derives this string, and for two different i's, let us say I and I plus 1, it cannot be that xi yi and xi plus 1 yi plus 1, these two strings are same. Why? Because x and y cannot be both empty together. So, therefore, it is very clear that in this case this A1 will generate infinitely many strings, and then of course, they will be starting from the start symbol S, because A1 is reachable, because G1 is a Chomsky normal form grammar, you will have some string starting from S with A1 in it, and now this A1 can derive infinitely many strings. So, therefore, S itself can derive infinitely many strings. So, the idea is fairly simple, and all that depended on is the fact that we have such a cycle, and we have crucially used the fact that the grammar G1 is a Chomsky normal form grammar. So, now we consider a very important problem, the so called parsing problem, that given a context free grammar G and a string x, you would like to know if x is in the language generated by the context free grammar G. Now, let me write this, that without loss of generality, we assume that this G is in Chomsky normal form. See, any grammar G, for any grammar G, we can create another equivalent grammar in Chomsky normal form, such that the two grammars will generate the same language except possibly the empty string. So, the only case that is left out will be the case of when your x is the empty string, but that can be handled separately, and will not spend any time on that, right. So, it is not too difficult to see whether epsilon is produced by an arbitrary grammar G, because all it means, see, remember that we define the set of nullable non-terminals, and if that means all those non-terminals which can derive the epsilon string, and if the start symbol happens to be nullable, then of course the language will contain epsilon. So, that's case of epsilon when when x is epsilon, that can be taken separately. Otherwise, we might as well can take that the grammar G is in Chomsky normal form. And now, the idea is, actually there are two algorithms we can talk of. One is a kind of brute force algorithm, and therefore it is extremely inefficient. So, let me just, without writing anything, let me just say what is that brute force algorithm. So, basically what you can do is you can keep enumerating the parse trees of the grammar G in increasing order of its length of its frontier, right. So it's not, it's of course messy, but conceptually it is fairly simple, right? And so as you keep generating the set of all parse trees of the grammar G, and once you cross the length of the string X, then of course no further parse tree could have produced X. By then, if you have not generated X as a frontier of one of the parse trees, then of course X is not in the language. However, you can see this will be an exponential time algorithm. As it happens, we have a far better polynomial time algorithm for this problem. And that is an interesting algorithm. It was given by, originally proposed by Koch, Younger, and Kasami. 3 people. So that therefore this algorithm is called the CYK algorithm. So we will describe what CYK algorithm is. Essentially, this is a dynamic programming algorithm. So suppose your X is the string, and without again loss of generality, we can assume X is a string of non-terminals, although I have just said the string X, but really speaking, we are interested when X is a string of terminals. So X, so let me right away say that X is in sigma star, where sigma is your set of terminals. So this is the string X, right? And let me identify portion of the, various portions of this string as, let me call this thing as Xij, this part, provided, and what is this way of naming substring, contiguous substring of the string X? What we mean is Xij is that part of X which begins at the ith position of X and is of length J. Okay. So there are two, this is indexed by this Xij. So what I mean is Xij is that substring of X, in fact the unique substring of X, which starts at the ith position of the string X and is of length J. Now suppose in some way, suppose we have a way of determining the set of non-terminals that can generate Xij. So let me call this set as Vij. So what is, so let me write it kind of formally. Vij is a set of all non-terminals such that A, these non-terminal, all these non-terminals derive the string Xij. And suppose we manage to do it for all possible values of I and j, right? Then it is quite clear that the string X is in LG if and only if V1n contains the start symbol where the input string X is of length n. I mean, this is just coming from the definition of this set Vij. So, it is saying Vij is the set of all non-terminals which can generate Xij, and the entire string X is, of course, the string starts at the position 1 and is of length n. So, Xij is nothing but, in this way of looking at, X is nothing but X1n. So, by definition, if S derives X1n, then of course the string X is in the language. And similarly, if S does not derive X1n, then it is not in the language, right? So, really we have not done anything much by stating this way. So, however, interesting thing is, what we require is, of course, we require therefore V1n, isn't it, in order to see whether the string X is in the language or not. Now, what we are going to do, and that is done in a typical dynamic programming paradigm, that we'll start with the smallest value of j for which we, these symbols are defined. And then, so essentially, first we define Vi1 for each I, then Vi2 for each I. See, the range of I in these two cases will be different, and this way we go on, right? Here I will range from 1 to n, here I will range from 1 to n minus 1, because at position n you can't have a substring of length 2 starting at position n. They can be only a substring of length 1. So, the point I am making is that this is the crucial point, that given Vij, I mean, let's write it slightly differently. We can define or determine Vij provided we already have the definitions of all Vik where k is strictly less than g. Of course, k can be not be less than 1, right? So that's the range. So I mean, we'll get into the details a little later, but already you can see the dynamic programming flavor of what we are trying to do. Because you see, these things are very easy to determine. What are VI1s? We'll see that. So the point is that from VI1, I will be able to determine VI2. From VI1 and VI2, I will be able to determine VI3. From VI1, VI2, VI3, I will be able to determine VI4 and so on. So this way we keep on building upwards for this index, and then finally we will be able to get the value of, we will be able to determine what is this set when j is n, and then we are through, right? We require V1n, and that is the dynamic programming approach, as you can see. Let us therefore prove this crucial thing. I mean, you see that if we can manage to prove this, that we can define a value for a value j, provided we have the definitions for all the j's which are less than this particular j, right? So this is what we said, that we can define Vij, the set Vij, we can, the set of non-terminals which generate the substring starting at I of length j, provided we know all those non-terminals which can generate for all Vik. Now see, basically here actually I'll not only need Vik but also, and let me just say for all I as well, right? Because I'm going to need, so let me write it this way, for all V Lk where k is less than j, where L is all possible values. So this is what we are saying. In other words, that if you are, this set, if you can define for a higher range, you can define for a higher range provided you know the definitions for lower ranges. So that's the basic idea, and let us see why it is doable. First of all, what is Vi1? Vi1 is the set of all non-terminals which generate the substring of length 1 starting at position I of the string x. So isn't it that Vi1 is essentially all those non-terminals A such that A goes to is a production where A is the ith symbol of x. This is very simple, right? Because Vi1 is basically string of length 1, and string of length 1 can be generated by some non-terminals directly using the production, and so we are saying Vi1 is essentially all those non-terminals A such that A goes to A is a production where this A is that substring of length 1 at position I, right? You know both I mean you know I, so therefore you know what is A, so you can just pick up this. So let us assume that I am talking of a string of substring of length j, right? And suppose this substring starts at position I, right? which all non-terminals can produce it. So suppose non-terminal A produces this, so I'll have, essentially what it means is that, I'm just writing it slightly differently, A is in V I J if and only if A can derive Xij, right? That substring of length j starting at position I. I mean, this is of course the definition of Vij. So we are saying A is in Vij if A can derive this. So consider this parse tree which generates Xij starting from the non-terminal A. Now, can this parse tree, can this tree, derivation tree, I mean, what can be the first production in this derivation tree? Can it be, see, remember in Chomsky normal form there are only two kinds of production. Either A goes to A where A is a terminal, or A goes to BC where these are two non-terminals. Of course, one of them can be, both of them can be same as A. So B and C in general, two non-terminals. So you will agree with me that if J is not equal to 1, then clearly this production cannot be the first production that we use here in this derivation tree. So it must be the case that we have used the production some A goes to BC in this derivation tree. Okay. So then this B will generate a left half of the tree and C will generate the rest of the, left half of the string Xij, and C will generate the rest of it. And this, let me say that this length is K. So what is this length is of course J minus K. Correct? So therefore, can you see what B is in terms of these Vij's? Which, so clearly B is a non-terminal which generates a string of the substring of length K starting at I. In other words, B has to be a member of, this implies that B is a member of V I K. And where does this string start from? What is this symbol? Not what is this symbol, but rather what is this position? This is clearly the position I plus K, right? Isn't it? So then similarly, when it is not difficult to see that C has to be a member of V I plus K, and as we said, this length is J minus K, so it is J minus K. Right? B is in V I K and C is in V I plus 1 K comma J minus K. So B, in other words, and by the way, what is K? What can K be? What is the smallest value of K? See, K cannot be 0. What would that mean? K cannot be 0 because that would mean that basically the C is generating this entire string and therefore B is generating the empty string. But in Chomsky normal form grammar, no non-terminal can generate empty string. So K has to be at least 1, and how big K is, for the same reason C can't generate, the part C generates in this derivation tree cannot be empty. So this is less than equal to, you can go j minus 1. Right? This k can range from 1 to j minus 1. And now you see that A is in Vij if and only if there exists. So let me say this. A is in Vij if and only if there exists B and C such that B is in Vik, C is in Vi plus 1 k comma j minus k, and A goes to BC is a production of the grammar. So do you see that, suppose, in other words, you just think of the other way, that suppose you have the definitions of V's, all V's, where the second index is less than, strictly less than j, right? Then surely, because you see the second index here I am using k and here j minus k, and in both these values are strictly less than j. So if I can have the definitions of VIKs such that k is strictly less than j, then I can determine whether or not A is in Vij, and therefore I can determine, I can take each of the non-terminals in turn and look at it, that whether or not it will be in this set, and therefore I can define the set Vij. In other words, this is the dynamic programming recurrence. I am not writing in that form, but you should be able to see that I can define Vij provided I have the definitions of VLK where k is strictly less than j, and that's the idea. So therefore, you see what we started off by saying that we need to prove this in order to get the basic crucial idea behind the dynamic programming algorithm, that now we have managed to demonstrate, that we can define Vij provided we already have the definitions of all VLK where k is strictly less than j. Therefore, you can see the CYK algorithm is going to be at the higher level very simple to describe. Your input is Chomsky normal form grammar G, string of terminals, and suppose the length of the string is n, then determine V1n and output yes, that means x is generated by G, x is in the language LG if and only if the start symbol of G, this start symbol S, is in V1n. So now all I need to do is to tell you in a more precise manner how V1n will be determined. So how do we determine V1n, which is what we need to do? First of all, we determine all the Vi1 for different values of I, and that is the same thing that we have written here, that Vi1 is this all those set of non-terminals A such that A derives small a is in P, this small a being the ith symbol of x. This is quite clear. Now what you are going to do, so therefore we have determined all Vi1, this length 1 things we have determined, and then we'll have this j will vary from 2 to n. The length now, the bigger lengths that we are considering, already length 1 v's are taken care of. So j will range from 2 to n, and we build up in that order. That's the dynamic programming. So j is ranging from 2 to n. So starting from 2, then 3, then up all the way up to n. What we do? We now once I have fixed a j, then for that j I define all Vij's. See, that's the idea. So, I can range in this once j is fixed with for some value, and clearly I can range from 1, isn't it? Such a substring can start from the first position of the given string x and all the way up to n minus j plus 1, right. So now we are defining Vij, and this is just to say that Vij is empty to begin with, because it can be empty, and then you see what I have written here is exactly the same thing that I am writing, that for k ranging from 1 to j minus 1. And this is what we had seen, if you remember, if you go back and you can see this, that k can range from 1 to j minus 1. That's exactly what we are writing here. K is 1 to j minus 1. The Vij is basically this set, and I am taking it with the old union, so that in case this is empty, this whole thing will become empty. That's fine. So, is the set of all A. See, it is like this, that we fix a value of k, get something and all that. So, what we are doing is that A, all those A, such that A goes to BC is a production, and B is in Vik and C is in Vi plus 1 k j minus k. That's exactly what we have written here, that this B part generates the string starting from I of length k for some value of k that we have set, and C is generating the rest of the string Vi plus k. So, therefore, C has to be in Vi plus k, because that string will start from this position, I plus kth position, and its length is going to be j minus k. That is what we have written. So, you see, so essentially we are saying that first C all those A's such that it goes to BC and B generates a length 1 string and C generates rest of the string, and then with that we take the union. The k is, as k is varying, we are getting different sets here, and all the we are taking their unions, and therefore finally when we come out of this loop, Vij would be determined, right, for certain value of j, and then we go to the higher value of j plus 1, and then j plus 2, and so on. And finally, when I manage to find the value n for j, then that is of course V1n, and then I look at whether the start symbol is in V1n. If so, I say yes, the string is generated by the grammar, otherwise I say the string is not generated by the given grammar G. So, that completes the description of our CYK algorithm, and in fact, as I have said, that this is an interesting algorithm, and we said also that this is a fairly efficient algorithm, at least it is a polynomial time algorithm. So, the time complexity of this algorithm is not too difficult to see. See, this part, this is a for loop, which is what? So, you are iterating, this for loop has, it will, this body will be, this body will be repeated n times, where n is the length of the string, right, length of the string x is n, and Vi1 is essentially what? How much time would you take to do this? Essentially, you are looking up the production set and the symbol A, and therefore, you can generate this. As you can see, this will be linear in the description of the grammar and x. And now, therefore, what will be the the determining time complexity determining factor for this algorithm is essentially this for loop, but this for loop has within it two other for loops. You see, this for loop, this range is n of the order n. This is again I can, it starts from 1 and the highest value is whatever j is starting from 2. So, n minus 1 again, that is order n, and since j can go all the way up to n, so this k can be at most of order n. So, you can see this entire loop thing will be done in order n cube, where n is the length of the string, and this body, what you are doing, you are looking up the production set, right, and you are looking up the already defined values of v's, and that again, to look up the production set, that will be of the order of that, looking at the production set would mean looking at examining G. So, again we can say this is essentially the time complexity will be determined by, bounded by n cube and multiplied by the size of the grammar. And if your grammar is already known, because often the problems are like that, that the grammar is fixed and you are essentially giving different strings, and to see whether that string is in the language or not, generated by the grammar. In that case, this length of the grammar G is a constant. So, therefore, we can see the time complexity is order n cube for a fixed grammar G. And when G is also in the input, so basically it is size of G multiplied by this n cube. And that n, see this n cube is coming from, this is the 3 nested loops, each one is of order n and hence n cube. So, that is clear. So, that completes the time complexity. It is a very simple time complexity computation for CYK algorithm. Thanks.